Hello everyone, today's problem comes from a viewer and it says, by considering the area or otherwise, show that if f of x increases strictly with x, then f of n minus 1 is less than the integral from n minus 1 to n of f of x is less than f of n. Okay, this one I'm pretty sure is very straightforward. Okay, so why is my ink so thick? Am I zoomed in? Yeah, let's fix that. Okay, so f is strictly increasing. So the integral of f of x from n minus 1 to n dx, this is less than the integral from n minus 1 to n of f of n dx, because what I've done here is I've taken a function and replaced it with something that's larger. Because f is strictly increasing, f of n is greater than or equal to f of x, and in fact it's a strict inequality except for at n. So this is because f of x is less than f of n for x less than or equal to n. For x strictly less than n. Okay, but this integral, f of n, is a constant with respect to the variable of integration, and the size of this integral, the width of that, is exactly 1. So this is just equal to f of n. And we can do the same thing for the other part of the integral, or the other part of the inequality. Again, if I replace f of x with f of n minus 1, this is again because f of x is strictly greater than f of n minus 1 for x greater than n minus 1. And this again, it's an integral of a function which is constant, and the length of the interval of integration is 1. So this is just equal to f of n minus 1. And so if we combine these, we get exactly the statement that we're asked about. If I wanted to show graphically why this is true, I mean, the question says by considering the area or otherwise. I mean, I did this with purely analysis-related results. But if that's n, and that's, well, no, I'll call this n minus 1. I'll call that n. The function is strictly increasing. That's not strictly increasing. Let's, something like that, okay? Well, the integral of this function from n minus 1 to n is the area underneath this. But f of n minus 1 is equal to that area, and f of n is equal to that whole area. So it's pretty clear that this overestimates this area, and that underestimates that area, right? The area, the integral of f itself is that piece. Yeah. So nothing too special there at the end. If you understand the relationships between how integrals preserve inequalities, then there was really nothing to this one. But also just graphing an arbitrary function as long as it's strictly increasing, and realizing it looks like the question's trying to trick you by writing f of n minus 1 and f of n. But keep in mind, when you integrate over an interval of size 1, if you integrate a constant, then that integral is just the value of the function itself. And so, yeah, it's a strange way of writing it because because it looks like you're comparing functions to integrals of functions, but in reality, the two pieces on the outside of the inequality, even though they're written as a function, they actually are supposed to represent the integral of that function, just so happens to be an interval of length 1. So nothing too much there. Yeah, thanks for the submission, and thanks for watching. Okay, I'm continuing a little bit with this question that I recently recorded. I didn't realize at the time that there's a follow-up part to this question. So I'll write down the original inequality that we ended up showing. And remember that this is something which is true when f is a strictly increasing function. And the follow-up question says, using the case f of x is equal to log of x, show that if n is greater than 1, then n minus 1 factorial is less than n to the n, e to the 1 minus n is less than n factorial. Okay, so my first thought here is to just substitute log x into this inequality and see what happens. It looks like we're not going to end up with exactly the inequality that we're asked to prove. Okay, so we need to show that n minus 1 factorial is less than n to the n, e to the 1 minus n, which is less than n factorial. Yeah, so the first thing I'm going to do is just make this substitution here and see what we get. I suppose exponentiating both sides will be something that we do. But then how do we get, maybe we have to do this for several values of n, and that's where the n minus 1 factorials will come from. I'm not completely sure. So this is going to be a little bit of plugging things in and playing around. Also keep in mind we have n greater than 1. I'm assuming that n should be an integer here, the way everything is written. I mean, we have factorials, so it's pretty much implied that n is an integer. N strictly greater than 1 means this is non-negative. Okay. Let's simplify what's in the middle of this inequality. Oh, what am I doing? This is not the right antiderivative. I'm mixing up integrals and derivatives here. So I think that should be the correct definite integral here. The antiderivative of log x is x log x minus x. X log x minus x. Okay, so let's simplify what we have here. And I mean, I noticed in the thing we're trying to prove, we have things of the form n to the power of n. So, bringing this into the exponent might be something that we want to do. And now I'm going to exponentiate all the way through. The exponential function is strictly increasing, so if I have 3 numbers that are ordered like this, then exponentiating will preserve the inequalities. Okay, and I think now I see where things are going. So I have that this is true for all values of n greater than or equal to 2. And what I want to do is I want to take this inequality. This is true when n is equal to 2. It's true when n is equal to 3. It's true when n is equal to 4, and so on. I'm going to multiply these all together because everything here is positive. Everything here is positive. So if I have this inequality, and think of n as being fixed, suppose n is equal to 2, but then I write down the exact same inequality and n is equal to 3, if I multiply everything column-wise, then the inequality will still be true. So the best way, another way that I'm going to see that, what I'll do is I'm going to replace n with k everywhere. And now I'm going to introduce with the product notation. So this is essentially doing what I said I was going to do. I'm just multiplying this whole expression by itself for different values of k. All right. So this thing on the left-hand side is just k minus 1 factorial. Sorry, n minus 1 factorial. And then here, there's a telescoping product thing going on. When I multiply terms like this together for different values of k, the numerator for one value will cancel with the denominator of another value. First, before I work that out though, I'm going to take this e to the negative 1 out in front, but it is of course being multiplied by itself n minus 1 times. So it's e to the negative 1 to the power of n minus 1. And yeah, that's the this is the other constant in the expression that we're looking for. And this expression is k factorial. Right? This is n times n minus 1 times n minus 2 and so on, all the way down to multiplying by 2. Of course, we can throw in multiplying by 1 to give us k factorial. Sorry, not k factorial, n factorial. There we go. And now I want to work on that. So this should just leave us with n to the power of n. That's this term for the largest value of k. Well, it's the numerator, because when k is equal to negative 1, the numerator when k is equal to negative 1 will cancel with the denominator when k is equal to n. So I'll also be left with divided by this expression when k is equal to 2. But that is, of course, 2 minus 1 to the power of 2 minus 1, which is just 1. So I'll get rid of that. Okay, less than n factorial. And this is exactly what we were asked to show. Yeah, so that's a nice little follow-up. It's not a direct, as you can see, it's not a direct substitution of this function, which gives us, from the original inequality. It doesn't give us exactly what we want. It ends up giving us this. But, I mean, the natural thing to do at this point, given what we want to show, we have an n minus 1 factorial on one side and an n factorial on the other. But in the thing we're working with, we have an n minus 1 and an n. The natural thing to do is just multiply these things by the same inequality, but for different values of n, decreasing all the way down to 2 or 1, depending on your point of view. And then it's just about verifying that this thing in the middle has the right cancellations to give us what we want. Yeah, I hope it's clear what I mean by the product notation here. This is exactly the same as the sigma notation for summations, except rather than adding these terms together for different values of k, we multiply them by themselves for different values of k. Yeah, so that was a nice little follow-up. And thanks for the submission, and thanks everyone for watching.